Yep, good afternoon, physicists. Last time we were looking at how Einstein was really trying to discover that when people are moving relative to one another, that is, you get two people in motion, what is it that they measure that is different, and what is it they measure that, they agree upon? And as long as they're not accelerating, we're going to assume that everybody has the same laws of physics. After all, it's that way on the Earth, even though, we really all do have different rotation rates, depending on your latitude on the Earth. And so we all have essentially, constant speeds relative to one another. And the laws of physics, certainly are the same, throughout the world and so forth. So, we're going to sort of assume that that's the case. And, looking at the Michelson-Morley experiment as well as Maxwell's, electromagnetic theory, Einstein really is banking on that it's the speed of light is the one thing that is the invariant. That is the thing that is constant no matter how you're moving. Right, so if you're moving very fast and you turn your headlights, those waves move away from you at the speed of light, 3 times 10 to the 8th meters per second. If you turn on some lights behind you, those waves move away from you at 3 times 10 to the 8th meters per second. You cannot add your speed to the speed of the wave. That's not how fast you are moving relative to that wave. So it's really the speed of light that is the constant. That's the one thing that everybody will agree upon, no matter what their motion happens to be, which then means that things like distances or lengths are not the same from one observer to the other observer. So if the speed is the same, then the lengths can't be, right? So space is really relative to a person's motion. And time is also relative. Time is not some sort of absolute where we all measure exactly the same amount of time for an event. Now, if we're all, on the Earth, watching something happen, maybe, some event that's, happening off the Earth, then we're all going to be measuring the same time because essentially we, are all kind of rotating, around the planet, the same way. But now if you're in a spaceship moving, at considerable speeds, watching some event that's taking place, in the heavens, people on Earth and then people on that ship will be measuring very different times because if the speeds are considerably different, right? So you really need to be hitting something like 10% the speed of light until you start worrying about relativistic mechanics. And so, it's the laws of electricity and magnetism that Einstein is saying is really, correct. It's the classical mechanics that we really need to kind of fix here. So today, special relativity, part 2, the fixing of classical mechanics. Now, if memory serves me, in 1905, Einstein's going to write, I believe, like 3 papers on special relativity, right? So all of this doesn't come out of just one paper, but he's able to show, and I think maybe I'm going to call this here, I'm going to call this relativistic mass. So even something like mass is not the same thing from one observer to another observer, okay? Mass is relative. And, we're all kind of measuring masses being the same here on Earth because, we just don't have a big enough relative speed, really between us or anything like that at all. And so I'm going to write this this way. So I'll put M and I'll put maybe like a little REL. So relativistic mass is really what we call rest mass. And the rest mass is exactly what it sounds like. It's the mass that you measure when the object is right in front of you and it's stationary. It's not moving relative to you and it's in the laboratory, right? So you get a book You can put it on a scale, you measure its mass, everybody in the classroom measures the same mass because that book is not moving relative to you, right? Now, if you get some sort of superhero that frisbees that thing, across, the campus, and, they throw it at half the speed of light, then, the mass of that object is different. So if it has collisions, if it interacts with any object, those interactions are not going to be conserved quantities with like energy, if it's an elastic collision, or with momentum, if you use the rest mass. You have to use this relativistic mass. And so what we really have is this rest mass all times gamma, which is this 1 over this v squared c squared. So this gamma factor is really this 1 over v squared c squared. So Einstein is able to show that something like this happens to be true. Now, take a close look at really what you've got here, because now you've got something in front of you that is telling you something really fundamental about the universe. And it really tells you that if the object has rest mass, right, if that number on the top, m with a little 0, is anything other than 0, then you can't really get the object going the speed of light. No matter how hard you push, no matter how close you want to get, you can get, but you just can't get that velocity at c. If the velocity goes to c, so take a look at this thing here. Right, so if we're looking at this, if the velocity goes to c, then what's happening is that you would have something like this on the bottom, right? So you'd have 1 minus 1, and that would imply that the rest mass would go to infinity. You'd be dividing something by 0. And so this tells us something very, very interesting, that the universe, for it to be really logically consistent, that it must have an ultimate speed. And that really is the speed of electromagnetic waves. Right? So we can get objects going the speed of light if they have no rest mass. But if they have anything other than 0 rest mass, then you're going to have some sort of limiting to how fast you can go. So essentially it's going to take something like a more energy than the universe has, because the object will attain really this kind of infinite inertia. Okay, so as you make objects go faster, they actually get harder and harder to push. Their inertia gets bigger. So if you imagine something like 1 proton and you start making it go fast, it's not like you start getting more and more protons there. Okay, it's that 1 proton becomes more and more massive. And let me hit pause here for a moment. I've got a dog here going nuts here. Okay, sorry about the brief pause in there. So what we've got here, though, is that mass, something like an object's inertia, is no longer a constant. Okay, so as an object, say like a proton, in an accelerator, zooms down the tube and goes faster and faster and faster, it actually gains more and more inertia. So it's not growing parts, right? The 1 proton is still there, but when it has collisions, when it has interactions, it does not act with the same mass as it had in those interactions as, when that object is at rest with us. And so that leads us to see that, when I look at this function here, that the universe has this ultimate speed. And for an object that has a non-zero rest mass, you cannot get it going the speed of light. Its mass becomes more and more infinite. And so it becomes, just harder and harder to do. And so this is where, I think Einstein really kind of realizes that, here's the fix, right? There was something wrong someplace. There's too many paradoxes kind of popping up here with the laws of physics as they stood in the, around 1890, 1900 and so forth. And so, recall here momentum. Okay, so let's get this guy here right here. And momentum here is kind of key. And this momentum that you have seen before, mass times velocity, is now considered kind of the classical definition of momentum, okay? And the reason why this is important is because really, one of our key laws when it comes to mechanics is really Newton's second law. That's written as, the sum of the forces vectorially equals mass times acceleration. And that acceleration can be written as a, dv dt. And that dv dt can be, or, the delta, dt, if we don't have differentials or something like that, is really sort of this mass times velocity. And so here is the classical definition. And so, Newton's second law can be written as really, right, the change of momentum with respect to time. Okay, so this right here is Newton's second law. And, certainly you have seen it referred to that way. And probably this is the way Newton would be writing it in the Principia most of the time, that the change of momentum per time, the rate of change of momentum, is coming from a net force. And so if there's a net force, as when you sum the forces on one side of that equal sign, when that number is not zero, then there is a momentum that is changing. Okay, now this law technically is incorrect. Excuse me. If we use really the classical, formulation here. Now, this will work if momentum, which is really mass times velocity, equals this mass, the object's true mass, and the object's true mass is based on really its velocity. And so its momentum is, based on its velocity. So if we use this momentum, the new modern momentum, then the law will work as far as we know all the time. And so, it's not really until you're able to control particles and make them go fast do we see that when they have collisions, that their momentum is completely different than their classical, mass times velocity expression here. That is, the mass is actually much, much more complicated. So this is really the fix here for really Newton's second law. So, what we really need to do is kind of write it as the sum of the forces equals kind of a rate of change. So kind of a ddt. So differential with respect to time, really mass times velocity. But the mass is all really times gamma here. That's 1 over the square root of v squared c squared. So if we write Newton's second law like this, now suddenly it works. And here then is really the fix that physics needs. Now classical mechanics really will work without any paradoxes showing up. And it'll work then brilliantly with, objects that are moving, which might be like an electromagnetic induction, where maybe like a magnet is moving towards a coil of wire and these types of things. That the forces, when really have to be, found this way, such that we really take care of really all situations that we might sort of really kind of run into, in nature here. So Newton now is seeing that, Einstein is seeing that, Newton's formulation is really kind of an approximation. F equals ma works as long as velocities are small. So if the acceleration does not allow the object to get a velocity that's probably more than 10% the speed of light, we may not see the difference, right? So a pitcher that throws a baseball at 95 miles an hour just doesn't get it going fast enough for us to see any difference here with the classical expression from some sort of relativistic expression. But when the velocities get big, then the differences start becoming very, very big. And so now we've got a way to really kind of fix up all of our classical physics and so forth here. So let's take a look at this example. A neutron has a rest mass of 1.67, and there are some decimals that come after that. Right now, I just decided to leave them off, but this is what we see in the front of the textbook. So 1.67 times 10 to the minus 27 kilograms. Find its momentum if it's moving at 1% the speed of light, and then at 95% the speed of light. Okay, so I think what I'm going to do here is I'm going to do this classically here. So momentum is something like mass times the velocity, and we're just going to have an object here kind of going in one straight line here. I'm not going to worry about angles or plus or minus signs or anything like that at all. So we've got a mass of 1.67 times 10 to the minus 27 kilograms. And it's moving at 1% the speed of light. Okay, so at that point, it really is kind of just a calculator issue. So I'm going to get 1.67 times 10 to the minus 27 times that by 1%, 3 times 10 to the 8th. And, I think I'm getting something like momentum here is like 5.01 times 10 to the minus 21, and that's kilograms times meters per second. Okay. Now, let me try this relativistically. Okay, so let's kind of change the game here, and let's kind of do the modern expression. Okay, so the momentum of a particle is going to be its mass times its velocity, but really all times gamma. Okay, so once again, it's really going to be mostly a calculator issue, but the mass 1.67 times 10 to the minus 27 kilograms times 1% of 3 times 10 to the 8th meters per second. Okay, and that's exactly what we have before. And now on the bottom, though, we have this 1% the speed of light. So I'm going to leave that in terms of c. Okay, so my c squares here are going to cancel out, right? Once I square the c squares, those are going to cancel out. But I do that 0.01, that's going to get squared. I'm going to subtract that from 1 and then take the square root of that. And so when I really kind of go down that road, what I have here on the top is that same number. Kilograms times meters per second. Now on the bottom, once I've taken the square root, I've got 0.9999, about 5 or something like that. And, when I sort of try this on the calculator, this comes out to be 5.01 to 3 significant figures times 10 to the minus 21 kilograms times meters per second. And so, at 1% the speed of light, I'm not really seeing, really any difference between, these numbers. So let's go ahead and try this now at 95% the speed of light and see exactly, what takes place here. Okay, so let's try this again here at 95% the speed of light. I think that's what we need to do here, right? Yeah, 95% the speed of light. Okay, so classically, let's do that. Yeah, I'm going to try to squeeze it over here on one side of the paper. Okay. So I've got 1.67 times 10 to the minus 27. Now times 95%, 0.95 of 3 times 10 to the 8th meters per second. Okay, so let me kind of see, what comes out of the calculator this time. So 3 times 10 to the 8th times 0.95 and times 1.67 times 10 to the minus 27. And I think my calculator is telling me just about 4.8 times 10 to the minus 19 kilograms times meters per second. So let me try that one more time. And yeah, it looks like I kind of get about the same thing here each time. So, okay, now relativistically, this particle is going now 95% the speed of light. And so this is a very relativistic object. So anytime we really kind of hit something over 10% the speed of light, we really should be considering using all of the new expressions, because we're going to be too far off typically if we don't. So 1.67 on top times 10 to the minus 27 times 95% the speed of light here. Okay, so there's the top, and I know exactly how that's going to calculate, right? That's exactly the same calculation that we've really got over here. But now on the bottom, what you're going to have is 1, and my velocity of the particle is 0.95 c. And that's going to get squared all over c squared. And so really now your c squares are going to cancel out. And so what I really have got is 0.95 squared. And subtract that from 1, the square root, and divided by 4.8 times 2 minus 19. And now I am getting, something considerably different here. So go ahead and try this on your calculator and see if you can't, get this number out with your calculator. So I'm going to try this one more time just to make sure that this all kind of works. And, I think I'm kind of getting something here that looks like 1 maybe 0.54 times 10 to the minus 18, I think, kilograms meters per second. So as long as I'm not doing anything wrong on the calculator, I think it kind of comes out something like that. And so, so now, we're not even in the same magnitude, right? We have different powers of 10. So now the air is, drastically different here. And so this is why we've got to use these new expressions here, because the air just gets bigger and bigger and bigger here. Okay, so Einstein is not done here with us. So so forces have been fixed up, and now it's time to look at this idea of energy, our other big, great concept when it comes to mechanics and so forth. And there's some new ways of calculating, old ideas, and there's some new ideas here, but nothing that is drastically difficult. But for the most part, an object, maybe I'll call it its total energy, according to Einstein, is going to be its rest energy plus its kinetic energy. So in other words, objects will have energy just because they're there. Okay. And so this right here really stands for the total energy. And this is the rest energy. This is without any motion at all. And then here is then the motion they have, or the energy they have because of motion, which is then the kinetic energy. Okay. Now, so, something that everybody has heard of, before they walk into this class is that an object's rest energy. Object's rest energy. So energy, maybe I'll put the rest energy here, is its rest mass times c squared, right? E equals mc squared, or that m0 is the rest energy. So this is the energy that it has when it has no motion. So here's the rest mass. And then that c is the speed of light. And this is pretty remarkable if you really look and see what is taking place here. Okay. What Einstein is showing us is that the universe sees energy and mass as really the same thing. Okay. They're different units, right? Energy is joules, mass is kilograms. But if we have this constant c squared thrown in here, then the units actually will work out correctly. And we have actually joules equals joules. But, I'm not worried about the constant right now as really looking at this conceptually, that nature, in terms of doing an accounting, is counting mass the same way that it counts energy. And so really our great law, of mechanics is what we call the first law of thermodynamics, that energy in closed systems is conserved. And this is just another type of energy. So objects have this type of energy just because they are there. And I'm going to show you, how the pros deal with this and the types of units that, they're going to use here on, a lot of this type of stuff here. Now, energy in one form of energy is really what we call light. Light has no rest mass, okay? But it can do work on objects, so it can move objects around. And so light has no rest mass, but it's worth a certain amount of joules, and it depends then really on the frequency of the light. And but something like this can happen. I'm just going to use some arbitrary units here just to kind of give you an idea of what's really kind of taking place here. So for example, what you can do here is that you can get, say, an electron, and let's say it's moving, and the electron has rest mass just because it's an electron, right? And we're going to probably see how to calculate that in a moment. But now, as it moves, it also has kinetic energy. And so let's just say that this thing has 100 units in some arbitrary system, not joules or anything, 100 units of energy. And that's its total energy. And what's common today is that we would get a positron, an electron with a positive electric charge, to collide with it. And let's have this one going the same speed, 100 units of energy. And what happens when an electron with positive charge and an electron with negative charge? One is called matter. The electron with the negative charge, what we call matter, because we find those around us everywhere. This is what makes up atoms. And then the electron with the positive charge is called antimatter. Now, when those two particles hit and they actually collide, their mass and all the little parts that they're made out of, if there's any parts there, electrons, there are certain classifications. So typically they're called leptons because we can't see that there's any structure to them. There's a charge distribution there, but those two particles disappear essentially from the universe, okay? And in that collision, what does appear is a photon, a single photon, a single particle of light. And that photon has 200 units of energy. Okay, so the mass can disappear. You go, well, that seems like something is disappearing from our universe, but what shows up is this photon that has the energy that the two particles had before. And then this photon, which has no rest mass, can shower into particles that have mass, right? So energy can turn into mass according to E equals mc squared. Mass can turn into energy. So in the original collision, mass of particles disappear and that mass turns into energy. And the pure energy form is the photon. Then the photon can actually turn into other particles. So it can turn back into an electron-positron pair. If you give it enough energy, it can turn into a lot of things that are heavier, right, than the electron and the positron combined. And so typically, this is what's done in the accelerators, is that you're trying to make very heavy particles that are not common. In fact, when I was at Stanford, we were making the WZ boson, and it doesn't exist anywhere in the universe. The universe is just way too cold to have W and Z bosons, but an electron and a positron hitting each other can create a photon of high enough energy. And there's a chance that when it showers into massive particles that you make this particle that you want. A lot of times that doesn't happen, but this is why you just keep doing trial after trial after trial after trial after trial. And these particles are just going nonstop, hitting each other and being recorded and so forth. But this is the idea of how energy is being really conserved in our universe. So in other words, something like mass now is worth some energy in our universe. And this is an idea that, as far as I know, nobody's really had before until Einstein is really kind of, pursuing this here with, his ideas of special relativity. And this all starts with those two ideas, that the laws of physics are the same for everybody, as long as nobody's accelerating, and that the speed of light is the same for all observers, regardless of their motion. And here's the physics that really comes out of those ideas. So we can look at time, distances, mass, and now energy. And with that mass, turn it into momentum and turn that into force. And all of these things that we've looked at before now are all really kind of getting fixed up here. And so we're looking at them a little bit differently, but there's nothing here that's devastatingly difficult or anything like that here at all. Okay, so I think what I want to do is show you how to handle an object's rest mass and so forth. So let me see if I have something here ready to go. Let's look at this. Protons at Fermilab were accelerated to 400 times the rest energy. So I put were past tense because Fermilab, I believe, is no longer an active accelerator, but this is near Chicago in Illinois. This was the big accelerator that America had running, and now we're giving money to the big collider in Europe. It's bigger, it can get things going faster and so forth. So it's a kind of a worldwide collaboration there. But at one time, protons at Fermilab were accelerated to 400 times their rest energy. What's the speed of those protons and what is their kinetic energy? Okay, so let's first worry about what is the rest energy of really the proton here. That's really, I think, the place to start here. Okay, and so I think I'm going to write it this way, that the rest energy, I'll put E with a little 0, is the object's mass times c squared. And when I look up a proton in the front of your book, right, it's a well-known number, 1.67 times 10 to the minus 27, which is very close to the mass of a neutron. The only difference really is in the decimal places. And so try this on your calculator. So mass times c squared. And this is going to then come out in some units that we should be familiar with. So I've got 27 minus times 3 to the 8. Okay, and I think I'm getting, this rest mass to be something like 1.50 times 10 to the minus 10. And what I've got here is kilograms, and then I've got meters squared seconds squared. Okay, so I'm going to try this in my calculator one more time, just to make sure. Calculator can act odds at times 1.67, 27 minus. Okay, so I'm getting the same thing. Okay, so these units here, take a look at those units. Kilograms times meters times, let's have this, meters per second squared times meters. How about that? Okay, so here's mass times acceleration. That's a Newton, and a Newton dotted into a meter is a joule. Okay, and so E equals mc squared really calculates joules. 1.50 times 10 to the minus 10 joules. Okay. Now, most of the time, the experts are not using this unit here because we just don't have a lot of intuition about times 10 to the minus 10 and these types of things. And so a change of unit is pretty typical in these situations here. And so I'm going to go ahead and do that. And we've all actually have seen this before because know that I've introduced this idea here that 1.6 times 10 to the minus 19 joules is called 1 electron volt. Okay, so that's going to cancel our joules. So I'm going to get that number, divide it by really the charge on an electron. And what I end up getting here, my calculator is 939,375,123 EVs. Okay, and so what people will do to make life a little bit easier is essentially call this 939 million MeVs. Okay. So the proton essentially has a rest mass of something like 939 MeVs. A little bit easier number to deal with. And I think if you do this with a neutron, you might get something like 940 MeVs, a number very, very close to this number here. Okay. Now, what's the speed of these protons? What's their kinetic energy and so forth? Okay, so what we're going to do here is develop a little bit of physics that we need to kind of handle really this situation here. Okay. And so really the total energy is the rest energy plus the kinetic energy. Now, Einstein is able to show that the total energy that a particle has is its rest energy, mc squared, all times gamma, which is this 1 over v squared, c squared. Sometimes that comes in to be handy. Sometimes, it's really not needed here. But for the most part, this right here is just, the total energy the particle has. You might have motion. If it doesn't have any motion, then that term is 0. It will always have this rest mass as long as, there's actually a mass that's not 0 when you measure it in the lab and it's just sort of sitting there. And we add those together and we get the object shearly, its total energy. Now, in this case, what we have is they're accelerated to 400 times their rest energy. Okay. What does that really kind of mean? They're accelerated to 400 times their rest energy. So typically the experts will look at that number 400 times their rest energy. And that's really the total energy that the particle has got. Okay. And so if I really look at it that way, that the total energy is somehow related to the rest energy by a factor of gamma, right? This is really just the rest energy, gamma here. And they're accelerated to 400 times their rest energy. So their rest energy is also sitting over here. And so we don't even need to know what that rest energy is in this case. It'll just cancel off both sides. I need to solve that for V, okay? And so, just be very careful with your algebra here, but I think you need to go 400, multiply both sides by this factor right here, and that all equals, I guess, 1, right? So we cancel out that E0 there. And so let's solve that for V if we can. So I think the next step that you're going to have here is probably something like this. And in this case, I may be trying to hang on to a lot of numbers really actually on my calculator. And I'm going to have to square both sides. So when I square both sides, I get rid of that square root. I guess I've got something like that. And so this is going to imply that, 1 minus this number right here equals V squared times C squared. Okay, so as long as I didn't really sort of lose anything here, I think this is probably looking okay. So, 400 squared, subtracting it from 1 is some number here on my calculator that is something like 0.99999,375. And I'm going to multiply both sides by C squared, and that equals V squared. And so what I'm going to do is take the square root of both sides. And when I hit the square root button, yeah, so, I'm getting 0.99999 about 7 C is the velocity of these particles. Okay, so Fermilab gets the protons going 99.9997% the speed of light or something like that to get them to have a total energy that's 400 times the rest energy. So decimals now suddenly are kind of important if you really want to kind of see what's taking place here. So you can kind of keep adding 9s here if you want, but the problem is, right, there's a curve, there's a function that you're fighting, and what you're fighting is that the object is becoming more and more massive the faster you get it going, which means that you have to push harder to get to more decimal places. But by doing that, you create that photon in the collision that is a photon that, as far as we know, there are no circumstances really in the universe right now that can create a photon of those energies. So even the photons that are created, in our sun are, pale in comparison to the photon that's created in, these colliders in terms of the energy. And so the particles that can possibly be cascading out of, that photon, are just something that just doesn't exist, anywhere in our universe any longer. The universe has been cooling down for billions of years, and so, we just don't have those particles anymore. Okay, so here's not a bad way of getting that velocity here. Okay, so there's a lot of 9s there. And let's kind of go back here and take a look and see what we need here. Okay, so what's the speed and then what's the kinetic energy of these particles here? And okay, so I've got some sort of issue here. All right. So let's take a look at this last part here. The kinetic energy. Okay, so the total energy, maybe I'll write it like this, is the rest energy plus the kinetic energy. And the total energy was 400 times the rest energy. And we have the rest energy here. And so, one thing you could do is just say it's 399 times the rest energy is the kinetic energy. And I think what I'll do is actually say 399, and then the rest energy of this particle is 939 MeVs is the kinetic energy of the particle. And so 399 times 939, and I get 374, about 700 or so MeVs is the kinetic energy of these particles. And since you're talking, hundreds of thousands of millions, you might start turning this into, actually billions or even trillions if you wanted to. But right now, I think I'll just, leave them like that. So, so here's the idea of, what's really kind of taking place here. That energy is still conserved. There's just this new idea that there's this rest energy, right? That mass to our universe is equivalent to numbers of joules. And so this idea will be used just a few decades later, after Einstein, publishes this in about 1905, and about the early 1930s, people start realizing that something happens in the nuclei of atoms. So 1905, we don't even have the concept really of the nucleus yet. It's still a year or two away before Rutherford probably does his very famous scattering experiment, and we start coming up with this idea of the nuclear model of the atom. But particles come out of the nuclei, and that's called radioactivity. A lot of atoms are stable, and all the particles just sit there for a long, long time. But some are radioactive, where there's just, you can almost think about it as like too many protons in there, right? And they're all trying to repel each other. And every once in a while, parts go flying out because you overcome the ability to kind of hold them together with this Coulomb repulsion. And when those particles come out, if you get those particles and you add their masses to what was there before, they don't add up to the same number. And so all the particles can be accounted for. So we're not losing protons, we're not losing neutrons, but there is energy differences. And so actually when the nucleus gets broken apart, there's an energy difference from it whole to breaking it, say, in half. And so when you break it in half, photons come out. That's energy. So all the particles can be attributed, but essentially mass is turned into energy to hold them together. And when you pull them apart, when you break it somehow, when you can split that nucleus by hitting it with something going really fast and it breaks apart, these photons come out. And so if you can do this and keep doing this, then photons keep coming out, and photons are energy. And we can use those to do work. And so then, you have a nuclear reactor. Or if you break enough of them apart, all almost simultaneously, and all those photons come out at once, now you've got a weapon. Now you've got an atomic bomb. And so, much of the physics is kind of laid down here in around 1905, but there is a lot of technical details of being able to try to get atoms that will, behave nicely in some sort of process like that and so forth. So eventually we'll be taking a look at the fission and the fusion reactions here as well. So give this some thought here, and hopefully this helps you kind of work through some of the sections here on special relativity here. That we need to look at nature a little bit differently, and in our lifetime, we're never going to be probably be a civilization that is moving at high enough speeds where these rules here become really kind of ingrained in our thinking, right? Probably it's only the nuclear physicists who are dealing with moving particles around at this speed. Are they thinking this way all the time? But these truly are the laws of physics for everything all the time. And the classical expressions that you learn are really kind of wrong, but they work pretty good at slow speeds. All right. So, big and, good enough for, most engineers and things like that. But, if you're an engineer that's working on a fusion project at, Lawrence Livermore Labs, okay, you're going to be well schooled into, relativistic mechanics and so forth. And, if you're an engineer working at Stanford Linear Accelerator, it would be the same thing, right? So, there are engineers that understand this and work with this, but for the most part, if you're an engineer that's designing a roller coaster for, some sort of new amusement park that's going in Texas, that railroad, that roller coaster car is going to be going 60 or 70 miles an hour down the hill, right? And you're just never going to be using anything like this. But we do now have a more consistent way of looking at nature, and it makes all of the paradoxes that I've mentioned before that you'll find in your readings that were just creeping up everywhere in physics. They all just go away. They're all going to be worked out now because we really have a new set of mechanics here. And so that's really what's taking place. So good luck on this, and I'll talk to you soon. And if you have any problems, just let me know, and we'll try to get to your issues and try to get them straightened out here. Okay.